Hey everyone, hello and welcome to yet another video. In today's video, we will take a look at a model that has been making the news in the NLP world, wav2vec 2.0. This is a framework for self-supervised learning of speech representations. This was released towards the end of last year by the Facebook AI team. And what's really interesting about this is that this paper claims to require way lesser training data than that is usually required for us to be able to train automatic speech recognition models. So I'll just quickly go through the abstract before we go on to the code implementation, which I've done using Huggingface. So we'll first take a look at the abstract. So the abstract says we show for the first time that learning powerful representations from speech audio alone, followed by fine-tuning on transcribed speech, can outperform the best semi-supervised methods while being conceptually simpler. And if you see here, I think somewhere they mention, while lowering the amount of label data to 1R, wav2vec 2.0 outperforms the previous state of art on the 100R subset, basically a 100x improvement, right, in terms of the amount of label data that is required. Using just 10 minutes of label data and pre-training on 53,000 hours of unlabeled data, we still achieve 4.8/8.2 WER. WER is word error rate. This demonstrates the feasibility of speech recognition with limited amounts of label data. And this is a very important problem, what do you say? This is a very important advancement because a lot of languages around the world don't have the kind of label data that you need to do automatic speech recognition, because what you need is basically speech samples and a transcribed text of what the speech is about, right? So that is not readily available for many languages in the world, and building that data set takes time, takes a lot of effort, takes lots of money, and this paper says that we can reduce that by a lot of margin, and that is why it's really exciting. Now let's quickly move on to the Huggingface wav2vec base 960H model. This is the model that has been trained by I don't remember the name, and that is not mentioned here, but it has been trained by somebody and uploaded, pre-trained by somebody and uploaded to Huggingface's models repository, and we'll be using this for our demo today. So what I'm going to demo today is basically, I've already recorded a hello world, basically kind of a sentence, just one sentence of about 30-40 seconds. I'll first play that out for you, and then we'll see how that gets transcribed using this wav2vec base 960H model. Okay, let me quickly see if I can play that out for you. And yeah, hello world.wav.
Hello world, this is a test.
I'm just going to play that out once again.
Hello world, this is a test.
Okay, so let's move on to the code where I had written this down, and I mean, I worked on this on a demo that somebody else had built, but I've tried to write down comments and put it in a more readable format. So let me just run these installations. Basically, you're checking for the Python version, NVIDIA SMA, and then I'm installing a few libraries that I will be using in order to get this demo going. Okay. I really like this new arrow that Collab is showing these days. Okay, so we've already installed the requirements. Now let me just import the libraries. I'm going to import NLTK, which is a natural language processing library. Librosa is a audio processing library. Arcparse, again Librosa, you don't need multiple times. Arcparse also I don't need right now, because Arcparse is mostly for taking in command line arguments. Import Torch. This is PyTorch. And this is a very popular machine learning, rather deep learning framework. Import sound file as SF. This is another library you can use to manipulate sound files. From transformers, import wav2vec wav2 for CTC and wav2vec to tokenizer, and these are the two functions we are going to use from the Huggingface library transformers. nltk.download.punkt, you need to download this in order to not run into any issues later. This is a tokenizer from nltk. So let's just import all of these. Okay, so we have run this cell. Now I have a few functions here. I'll just run these functions first. And run the code first, and then we'll go through each of that. So this now starts downloading the model onto the machine. Okay, error opening hello underscore world.wav. That's probably because it doesn't exist here anymore. So what I could do is go to downloads, say hello underscore world.wav and put it here. Yeah. So you need to upload your sample file, and run this again. Okay, let me rename this to hello underscore world. Okay, we have a transcribed version over here. It says hello world, this says a test. And what I had said was hello world, this is a test, and this was what we were able to transcribe. Now quickly let me take you through the functions. So this is where we are giving the file as input, so hello underscore world.wav, and this is what I had uploaded. Then I'm calling this load underscore wav2vec underscore 960h model function, and this function returns a tokenizer and the model. Let me just quickly take you to that function. This is the function. So it returns the tokenizer and the model from pre-trained tokenizers and models. What it does, it goes and fetches. So Huggingface maintains a repository of different models from Bert to Roberta, and all these kinds of NLP models, right? So every new model that comes out, Huggingface almost has it in a week or so. It's really fast that way. So we have a pre-trained wav2vec based 960h model, which if you see here it in more detail, the base model pre-trained and fine-tuned on 960 hours of library speech on 16 kilohertz sample speech audio. When using the model, make sure that your speech input is also sampled at 16 kilohertz. So this is the model we are using, and yeah, this has been pre-trained and fine-tuned on 960 hours of library speech on 16 kilohertz. Okay, so this is the model that we are fetching here, and this is the tokenizer that we are using. Okay, so after I call this function ASR underscore transcript, automatic speech recognition underscore transcript, and we here give tokenizer, model, and the wave input file as parameters. And if I show you that function here, okay, so returns the transcript of the input audio recording. Your output is the transcribed text. Your input is your tokenizer, model, and WAV file. So you're reading the file, and that is the WAV file. You're getting the speech and sample rate, making it one-dimensional because your input is supposed to be one-dimensional array, and then you're resampling it to 16 kilohertz. And like we saw over here, when you're using the model, make sure that your speech input is also sampled at 16 kilohertz. So we are resampling it to 16 kilohertz, tokenizing it. This is PyTorch, getting the input values from basically tokenizing and getting the tokenized values, taking logits over it, and after that take an argmax, which is basically finding the most probable word ID out of all the predicted IDs, and then we take these predicted IDs and decode using the tokenizer to get the transcription. Okay, and this is how we are able to get the transcription. But the transcription, once you take the argmax and then you decode using tokenizer, is all caps. What you saw as the output was not all caps, it was hello world, this is a test. So what we've done here is that we've tried to correct that using correct uppercase sentence function. So we first change the transcription to lower, and wherever we need to uppercase, we uppercase, and this is the function that does that for us. Okay, we tokenize the sentence, and then for the first word we capitalize and return that over here. So this is the transcription you see, and at the end of this function you just return this transcription after all of this processing has happened. And then basically store that as text over here, and then we just print this text. And this text gives you hello world, this is a test. Now this is not very accurate. We could perhaps train it on more data, or actually we don't really use a language model here, right? So most of these problems are solved by using a language model at the end. So perhaps trying that out along with this could be a useful thing to do. But that's it for now. I mean, we've seen the journey from giving a wave input file as wave file as input to seeing a transcribed text output using Facebook's wav2vec model that has been pre-trained on and uploaded on Huggingface. So this is what we've seen today, and I hope this video was useful for you to take a look at how you could also train your automatic speech recognition system using this model. I'll be sharing the links of all of these things that we've seen today in the description box below. Thank you so much for watching. Please do subscribe to the channel and keep supporting like you have always done. Thank you.